Right now, somewhere in China, engineers are working on a wireless technology that could make the fastest internet connection you have ever used look painfully slow. Not 5 times faster, not 10 times faster. We are talking about a completely different level of wireless communication, where data could move through the air at speeds that make today's 5G networks look like technology from another era. And the strange part is that the biggest breakthrough may not even be the speed. It may be the technology underneath it. Because researchers are no longer simply trying to make 5G faster. They are looking beyond 5G entirely. They are experimenting with frequencies that were once considered too difficult to control, developing new kinds of chips, combining artificial intelligence with wireless networks, and pushing communication into a part of the electromagnetic spectrum that could eventually carry enormous amounts of information through the air. This is the race towards 6G. And China is moving extremely aggressively. But before we talk about what China has built, you need to understand why 5G itself has reached a fundamental limit. Because the problem is not that 5G is slow. The problem is that the wireless spectrum we have been using for decades is becoming crowded. Think about the air around you right now. You cannot see it, but it is filled with invisible signals. Your phone is communicating with a tower. Your Wi-Fi router is sending data around your house. Bluetooth devices are talking to each other. Satellites are transmitting information. Cars are communicating with sensors. Factories are controlling machines wirelessly. Millions of devices are competing for space inside the same invisible environment. And the number of connected devices is exploding. Every generation of wireless technology has tried to solve this problem by becoming more efficient. 2G made mobile communication practical. 3G made mobile internet possible. 4G transformed smartphones into miniature computers. And 5G was supposed to take the next massive step. The promise was enormous. Self-driving cars communicating with each other in real time. Factories filled with robots connected wirelessly. Remote surgery, smart cities, immersive virtual reality, machines that could communicate almost instantly. But there was a problem. The 5G experience most people actually have is very different from the 5G that was advertised. Your phone may show a 5G symbol at the top of the screen, but that does not necessarily mean you're receiving the extreme speeds engineers demonstrated in laboratories. In many places, the network still depends heavily on frequencies that are not dramatically different from earlier cellular systems. And the fastest 5G frequencies come with a serious weakness. They do not travel very far. They can be weakened by buildings. Trees can interfere with them. Rain and atmospheric conditions can create problems. Even the physical layout of a city can determine how well the signal works. So you end up with a strange trade-off. Lower frequency signals travel farther, but carry less data. Higher frequency signals can carry enormous amounts of information, but struggle to travel through the real world. That trade-off has existed for generations, and 6G is essentially an attempt to break it. This is where things become interesting, because instead of simply squeezing more performance out of the frequencies used by 5G, researchers are looking much higher, much higher, into the terahertz range. Terahertz frequencies sit between microwaves and infrared radiation, and from a communication perspective, they are incredibly attractive. Why? Because higher frequencies can potentially provide much more bandwidth. And more bandwidth means more information. Imagine the difference between a narrow highway and a massive highway with dozens of lanes. The cars can travel at similar speeds, but the second highway can move vastly more traffic at the same time. That is essentially what researchers want from the next generation of wireless communication. They want more space, more bandwidth, more capacity, more devices, more data, and almost instantaneous communication. But there is a reason nobody simply switched to terahertz years ago. It is incredibly difficult. The higher you go in frequency, the more complicated the engineering becomes. Signals can be absorbed by atmospheric moisture. Objects can block them. The useful transmission distance can become extremely short. And creating hardware capable of generating, controlling, amplifying, and receiving those signals is extraordinarily difficult. For decades, this region of the spectrum was sometimes described as a technological gap. Scientists knew the potential was there. But turning that potential into a practical communication system was another matter entirely. It was like having a road that could theoretically carry millions of vehicles, but no engine powerful enough to get the cars onto it. That is the problem researchers have been attacking. And China has been investing heavily in solving it. One of the most important developments involves something much smaller than a communications tower: a chip. Because there is a hidden problem inside every wireless network. The tower itself is not just one machine. It contains multiple systems handling different frequencies, signals, filters, amplifiers, converters, antennas, and processing tasks. The higher the frequency becomes, the more difficult those systems are to build. So if 6G is going to work at extremely high frequencies, engineers need new hardware. They need components that can operate at frequencies far beyond the range of traditional wireless electronics, and they need those components to become small enough, efficient enough, and affordable enough to eventually deploy across massive networks. This is where photonic technology becomes extremely interesting. Instead of forcing everything to happen electronically, researchers can convert electrical signals into light, and light can carry enormous amounts of information. Think about fiber optic internet. The reason fiber can move so much data is that it uses light rather than traditional electrical signals. Now imagine taking some of that philosophy and bringing it into wireless communication. A system can generate a signal, convert it into an optical representation, process it using photonic technology, and then convert it back into a radio frequency signal. That can potentially allow one system to handle multiple frequency ranges far more efficiently than traditional hardware. And researchers in China have been working on exactly this kind of technology. The goal is not simply to make one faster wireless connection. The goal is to create hardware capable of handling many different frequencies, using a much smaller and more flexible architecture. That matters because future networks will not operate on one frequency. They will need to dynamically move between different parts of the spectrum depending on distance, interference, data requirements, and the environment. Imagine your phone communicating with a nearby tower using one frequency for maximum speed, then switching to another frequency when you move behind a building, then using another band when the network becomes crowded, then using an extremely high frequency channel for a burst of enormous data. All of this could happen automatically. You would not see it. You would not even know it was happening. Your device would simply remain connected. And this is where artificial intelligence enters the picture. 6G is not expected to be just a faster radio network. It is increasingly being designed as an intelligent network. Instead of having towers follow a fixed set of rules, AI could analyze traffic, interference, device movement, environmental conditions, and available spectrum in real time. The network could essentially decide how to communicate with every device. Imagine a stadium containing 50,000 people. Every person has a phone. Thousands of people are uploading video. Others are making calls. Some are streaming live broadcasts. Security cameras are operating. Drones may be flying overhead. Connected vehicles are nearby. A traditional network sees enormous congestion. A future intelligent network could continuously reorganize itself. It could detect where the demand is increasing. It could redirect resources. It could change frequencies. It could alter signal patterns. It could even predict where the network will become congested before it happens. That is one of the fundamental ideas behind 6G. The network itself becomes intelligent. And that changes what wireless communication can be used for. Because once communication becomes fast enough, reliable enough, and responsive enough, the network stops being just a way to access the internet. It becomes infrastructure for machines. Imagine thousands of industrial robots working together. A robot picks up a component. Another machine moves into position. A camera detects a defect. The system analyzes the defect. Another robot changes its operation. All of this can happen continuously. The machines do not have to wait for a human operator. They can coordinate with each other through the network. That is the vision behind the industrial side of 6G. But factories are only the beginning. Consider autonomous vehicles. A self-driving car does not only need sensors on the vehicle, it could potentially communicate with other cars, traffic systems, road infrastructure, pedestrians, drones, and cloud-based intelligence. The more quickly that information moves, the faster the system can react. A car approaching an intersection could receive information about another vehicle before its own sensors even have a clear view. A traffic system could adjust signals dynamically. Road infrastructure could communicate hazards. And entire transportation networks could behave more like one connected system. Now take that idea into the air. Drones, thousands of them. Delivery drones, inspection drones, emergency response drones, agricultural drones, surveillance and mapping systems. Today, operating large numbers of autonomous drones is difficult because communication, control, and coordination are still major challenges. A future network designed for massive machine-to-machine communication could make those systems much more practical. And then there is something even more futuristic: holographic communication. Today, when you call someone, you see a flat image of their face. Even a high-quality video call is still a rectangle. Your brain has to interpret depth from a two-dimensional image. But if networks become capable of moving enormous quantities of data with extremely low latency, three-dimensional communication becomes much more realistic. A camera system could capture a person's shape from multiple angles. That information could be compressed, transmitted, reconstructed, and displayed as a three-dimensional representation somewhere else. You would not simply see someone's face on a screen. You could potentially see their entire three-dimensional presence. This is one reason 6G is being discussed as more than a telecommunications upgrade. It could become a new interface between the physical and digital worlds. But there is a catch, and it is a very important one. None of this means that 6G is already replacing 5G. It is not. The transition is going to take years. 5G infrastructure is still being built and upgraded across the world. Companies have invested enormous amounts of money into it. Phones, towers, network equipment, and industrial systems are designed around it. No telecommunications company is going to throw all of that away overnight. Instead, 6G will likely develop alongside 5G. The early systems will probably appear in specialized environments: research centers, factories, airports, universities, large cities, industrial zones, military and aerospace applications. Eventually, as the hardware becomes cheaper and standards become established, consumer networks can begin adopting the technology. That is how every previous generation evolved. But China has one enormous advantage: infrastructure. China already built one of the world's largest 5G networks. That means the country does not have to start from zero. It already has towers, fiber connections, manufacturing capacity, telecommunications companies, research institutions, millions of engineers, and a huge domestic market where new technology can be tested. That combination matters, because developing a technology is one thing. Deploying it at national scale is something completely different. A laboratory can demonstrate a 6G connection, but connecting hundreds of millions of people is an entirely different challenge. China has already demonstrated that it can deploy telecommunications infrastructure on an enormous scale, and now it is trying to use that experience to move toward the next generation. This is why the competition has become global. The United States is investing in advanced wireless research. South Korea is working on its own 6G programs. Japan is developing next-generation communication technologies. European research groups are working on future wireless standards. Major companies such as Samsung, Nokia, Ericsson, Huawei, and others are all looking at what comes after 5G. Because whoever leads 6G may gain much more than faster internet. They could influence the standards that the rest of the world eventually adopts. And standards are incredibly important. Think about the charger on your phone, or Wi-Fi, or Bluetooth. Devices from different companies can communicate because everyone follows technical rules. Wireless networks work the same way. If one country's technology becomes dominant, its companies can gain enormous influence over the global supply chain. That means patents become important, chip designs become important, network equipment becomes important, and the standards themselves become important. This is why the 6G race is not simply a race between scientists. It is also an economic competition, a manufacturing competition, a semiconductor competition, and increasingly, a geopolitical competition. Because the country that controls the technology underneath the network can potentially influence everything built on top of it. Imagine a world where autonomous vehicles depend on wireless infrastructure. Factories depend on wireless robotics. Hospitals depend on ultra-low latency connections. Cities depend on connected infrastructure. Drones depend on constant communication. And businesses depend on massive real-time data networks. Whoever supplies the underlying technology suddenly has enormous strategic importance. That is why the 6G race matters. But there is another problem that engineers still have to solve: coverage. Because the incredible speed of extremely high-frequency signals comes with a price. They do not travel through the environment as easily as lower-frequency signals. A wall can become an obstacle. Rain can become a problem. Humidity can reduce performance. A person standing between the transmitter and receiver can potentially interfere with the connection. So how do you build a city-wide network using signals that do not naturally travel very far? You use more transmitters, much more. Instead of relying on a small number of giant towers, future networks could use enormous numbers of smaller access points. Buildings could become part of the network. Street infrastructure could become part of the network. Vehicles could become part of the network. And intelligent systems could continuously determine which transmitter should communicate with which device. The network becomes dense. But that creates another challenge: energy. Millions of transmitters require electricity. The more data the network moves, the more processing power is required. And if 6G is going to connect billions of devices, energy efficiency becomes absolutely critical. That is why researchers are not only chasing speed, they're also trying to reduce power consumption. They want smarter antennas, more efficient chips, better signal processing, intelligent resource allocation, and systems that can shut down unused components when demand is low. The future network cannot simply be faster. It has to be smarter, it has to be more efficient, and it has to be capable of adapting to its environment. That is where AI becomes one of the most important pieces of the entire puzzle. Imagine a network that knows when you're moving. It knows when a stadium is filling up. It knows when a factory is beginning a production cycle. It knows when thousands of people are leaving a concert. It knows where the next demand spike is likely to occur. Instead of reacting after the network becomes overloaded, it prepares before the overload happens. That is the difference between a network that simply transmits data and a network that understands what is happening around it. And this could eventually change the definition of a mobile network. Your phone would not simply connect to a tower. It could become part of a giant intelligent ecosystem. Cars could communicate with roads. Robots could communicate with factories. Drones could communicate with each other. Satellites could communicate with terrestrial networks. Sensors could continuously report environmental information. And AI systems could coordinate everything. The result would be something much bigger than faster downloads. It would be a nervous system for the physical world. Even tiny amounts of latency can make remote control difficult. Now imagine remote construction, remote mining, remote disaster response, remote medical systems, entire machines controlled from another continent. That sounds futuristic. But wireless communication is gradually moving in that direction, and China wants to be one of the countries defining how that future works. This is why the 6G race is becoming so intense, because 5G was never really the final destination. It was a bridge between traditional mobile networks and something much more powerful. 6G is trying to build the next layer. And the most surprising part is that the breakthrough may not come from one giant invention. It may come from dozens of smaller breakthroughs happening at the same time. Better chips, better antennas, better materials, better signal processing, better AI, better optical systems, better satellites, better manufacturing. Put all of those improvements together, and suddenly the network becomes capable of things that seemed impossible only a few years earlier. It has invested in advanced wireless research. Its universities and companies are working on terahertz communication. Its engineers are developing new photonic and semiconductor technologies, and it is pushing toward early-stage 6G demonstrations while the global standards are still being developed. That does not mean China has already won. It does not mean every claim surrounding 6G will become reality. And it certainly does not mean 5G is about to disappear. But it does mean the competition has started much earlier than most people realize, because when you look at the headlines, it is easy to think 6G is something that will arrive around 2030. But the real race happens years before consumers ever see a 6G logo on their phones. It happens inside laboratories, it happens inside chip factories, it happens inside standards meetings, it happens in patent offices, it happens when governments decide which technologies receive billions of dollars in funding. And it happens when engineers discover a way to make one impossible problem slightly less impossible. That is where the real race is happening right now. And if the researchers succeed, your next wireless connection may feel completely different from today's internet. You may not even think of it as a network. It could simply become the invisible infrastructure surrounding everything. Your car, your phone, your home, your workplace, your city, your machines. Everything connected, everything communicating, everything responding almost instantly. And that raises the biggest question of all. What happens to 5G? The answer is probably not that it suddenly disappears. Instead, 5G may become what 4G eventually became, a mature technology that continues operating while the next generation handles applications that require much more performance. Your old 4G phone did not suddenly stop working when 5G launched. The same thing will probably happen with 5G. It will continue serving billions of devices. Meanwhile, 6G will slowly take over the applications that need its unique capabilities. But once the new technology becomes affordable and widespread, the transition could accelerate rapidly. And then we may look back at today's internet the same way we look at 3G today. Slow, limited, primitive. Because the history of wireless communication has always followed the same pattern. First, something seems impossible. Then engineers build a prototype. Then someone proves it can work. Then companies begin investing. Then governments begin competing. Then infrastructure gets deployed. And eventually consumers wake up one morning and realize that the technology has completely changed around them. That is where 6G is today. Somewhere between the laboratory and the real world, between impossible and inevitable. And China wants to move that boundary faster than anyone else. The question is whether it can. Because if it does, the next revolution in wireless communication will not simply make your phone download a movie faster. It could connect the physical world in a way we have never seen before. And the strange thing is that you probably will not notice when it begins. There will be no giant switch. No single day when 5G suddenly dies. Instead, more devices will connect. Networks will become smarter. Latency will fall. Factories will become more automated. Cars will communicate more intelligently. Drones will become more autonomous. Three-dimensional communication will become more realistic. And slowly, almost invisibly, the world around you will become part of the network. That is the real promise of 6G. Not simply faster internet. A world where communication becomes so fast, so intelligent, and so deeply integrated into physical reality that the network itself almost disappears. And if China manages to lead that transformation, the biggest question will no longer be whether 6G is faster than 5G. It will be who controls the technology that connects the next generation of machines, cities, vehicles, and people. Because the country that wins that race may not just have the fastest network. It could help define the rules of the connected world for decades. And that race has already begun. So the next time you look at that little 5G symbol on your phone, remember something. It may look like the future, but somewhere in a laboratory, engineers are already building what comes after it, and if their experiments succeed, the wireless world you know today may soon look as outdated as 3G. The era of 5G is not ending tomorrow, but the race to replace it has already started, and the country that reaches the finish line first could have a very different kind of power in the next decade.